The presentation of the jury I will do in French and then
Okay.
switch in English.
Ok, pas de souci. Oui, pas de souci.
Bonjour à toutes et à tous, à ceux qui sont présents et à ceux qui sont en ligne. Peut-être qu'il faut que je prenne le micro. Donc, j'ai eu l'honneur d'être désigné président de ce jury. Je suis Alexis DESCHAMPS, professeur à Grenoble INP, chercheur au laboratoire de CIMAP. Et donc, on va commencer par présenter rapidement le jury. Donc, on va commencer par ceux qui sont présents.
À l'université Grenoble-Alpes et membre du laboratoire CIMAP.
Jean-Jacques BLANDIN, je suis chercheur au laboratoire CIMAP et puis j'ai participé à l'encadrement de la thèse de Akash.
Jean-Marie DREZET, moi je suis professeur à l'École Polytechnique de Lausanne et puis je suis rapporteur de cette thèse. Guilhem ROUX, donc je suis ingénieur-chercheur au CEA et encadrant aussi de cette thèse.
Merci. On peut continuer avec celles et ceux qui sont en ligne.
Du coup, tout le monde, on peut, everyone is able to hear us, so it's okay. Yeah.
Ok. Aude?
Oui, Aude SIMAR, professeur à l'Université catholique de Louvain en Belgique.
Et pour finir, Marc?
Professeur.
Oui, vas-y.
Ok, go. Vas-y.
Marc Thomas, donc à l'ONERA. Je travaille à l'ONERA au département matériaux et structures.
Ok, merci à tous. Donc pour ceux qui sont présents, veillez à ce que vos portables soient éteints. Et ceux qui sont à distance, que vos portables soient allumés. Okay, so we're here to hear your PhD defense now.
Is it okay if I keep the mask or everyone?
It's, okay, it's fine for me. So we'll first hear you for about 45 minutes to present your work,
Yes.
Akash Sonawane, on structural aluminum alloys processed by laser powder bed fusion.
Yes.
And then we'll go on with the questions of the jury. So please go on.
So good morning, everyone. Thanks for being present here for my PhD defense. So to start with, today I will be presenting my PhD work, which is structural aluminum alloy processed by laser powder bed fusion, a fundamental understanding of cracking. So the thesis was performed under in joint collaboration between CA Grenoble and CIMAP Laboratory of Grenoble University's Alpes, under the supervision of Dr. Guilhem ROUX, Dr. Guilhem MARTIN, and under the direction of Professor Jean-Jacques BLANDIN. So to start with the content summary of my presentation, first I will go into the introduction, the materials and methodology used in the study, the results and discussion, and finally I will be presenting the conclusion and perspectives. So to start with the context of study, most of the traditional processes, like for example, casting and welding, they have some key issues related to, for example, you have materials wastage, they need a lot of machining step required, they have less design flexibility. So to address this issue, let's think about additive manufacturing technologies. For example, here the laser powder bed fusion, L-PBF process, which we used in the context. So with the laser, basically you are melting the powder material, and due to the rapid solidification at very high cooling rates, for example 10⁶ Kelvin per second, you end up having very finite micro level melt pools, which leads to you can have design flexibility with this process, and you can end up getting direct fabrication of products. So now if we are looking into the additive manufacturing of aluminum alloys, for example. So for example, the casting family, which is the most used in additive manufacturing of aluminum alloys, like the LSI 10 mg and LSI 7 mg, for instance. So if we do L-PBF of these particular alloys, it's very easy to process, and you can get complex structures, you can get complex parts directly out of it. If we look into the structural aluminum alloy, for instance, the 6061 aluminum alloy, which has magnesium and silicon as its major alloying elements. If we do the L-PBF of structural aluminum alloys, we tend to get a lot of cracks, and it's very difficult to process. So now several strategies can be thought of to solve the problem of cracks. For example, the first one can be the solute content modification, which is very much reported in literature, like adding zirconium and scandium to induce heterogeneous nucleation sites, and basically this gives you grain refinement, and this leads to cracking mitigation. The second way can be thought of is the process modifications. For example, changing the laser power, laser speeds, the preheating, the scanning strategy, basically to change the solidification conditions like thermal gradients and solidification velocity. But not much work has been done in this part of the strategy. For example, there are not many literature which report cracking mitigation due to process modifications. So my thesis is focused on this particular aspect of the process modifications. So basically the goal is to understand the fundamental mechanism of cracking, and if it's possible to produce guidelines to mitigate cracking. And the second is as well to understand if process optimization can produce us crack-free samples or not. So moving into the materials and methodology section. So to start with describing the powder characteristics, for example, of the 6061 aluminum alloy. Here is the first composition. There is the standard composition of the 6061 aluminum alloy and the powder which we use, the actual composition. So the composition is quite in the range of the standard. In terms of morphology, the gas atomized powder, we clearly see that you have some satellites, you have spherical shape of the powder, and the powder morphology is polycrystalline in nature. In terms of size distribution, the powder was quite good in terms of the requirement in L-PBF is going from 20 to 60 microns, and we had that size distribution achieved with our powder. In terms of flowability, because flowability of the powder is also an essential criteria to be in the L-PBF, because if your powder is able to be in good flowability character, it can be producing good dense parts, for example. So we classified this flowability, we quantified this flowability based on a Hausner ratio, which came out to be quite good, and that's how we concluded the powder was good in flowability. So all these criteria were fulfilled in order to be used in L-PBF. Now the methodology of the work. So we started with the powder. We did some 1D analysis, 2D tracks analysis with the laser tracks. So the goal was to just identify stable melting conditions. And based on the stable melting conditions, we can identify the process parameters, for example, which laser power and which laser speeds need to have to attain the stable melting conditions. And once we have that, we can print 3D printing cubes and finally identify the best optimized parameter, for example. So by optimized parameter is like we need, the goal is to achieve the highest relative density, dense sample, assuming that stable melting conditions are providing dense samples. And the second is whether the stable conditions, they give cracking mitigation or not. So moving into the results and discussion of this processing optimization methodology. To start with, we did some basic single track analysis, and we studied the melt pool dimensions, for example, the length to width ratio as a function of linear energy density. Linear energy density is nothing but the laser power, the ratio of laser power to laser speeds. So we can see clearly a rectangular hyperbola. So for example, if you are at low energy, you have high length to width ratio. And if you are at high linear energy density, your length to width ratio decreases. So basically for low energy densities, for low power, low laser speeds, for example, we found two particular conditions, which are basically instabilities due to high speed. So these instabilities are basically balling and humping. So what is happening is when you have sufficient high laser speed, you tend to disintegrate the melt pools in order to maintain the minimum capillary pressure inside the melt pool. So these are instabilities due to high speed. If you are sufficient high linear energy density, you can get a stable melt pool condition. For example, you have a continuous single track as shown in the green figure at the bottom. So we need, in order to avoid balling and humping, we need particular high linear energy density. If we look the similar different conditions in terms of the processing map, for example, the y-axis is laser power and the x-axis is laser speeds, for instance. So if we are sufficient high energy, for example, you can end up also getting unstable melting conditions. So this can be due to the intense convection flow due to the high laser energy density. If you are low in low energy density, for example, low powers, you can get into unfused region. If you are at sufficient high laser speeds, you can get humping and balling as explained in the previous slide. And there can be a particular stable melting conditions, as we have identified the green zone here. So this was identified in the 1D track analysis. Now, similar processing map was identified for the 2D conditions. So 2D condition basically was to understand what is the effect of when a laser is passing just adjacent to this previous laser track. So similar conclusions were found out using the 2D analysis. So now, okay, we have identified stable melting conditions. So now let's try to and see what is its effect on when we finally 3D print the cubes. So for finally 3D printing the cubes, we chose a simple scanning strategy without any rotation between the two layers. So the choice of this strategy was basically to have simple microstructure which are easy to be interpreted. So based on the stable processing conditions, we saw, okay, let's analyze what is the density of sample as a function of linear energy density. So the density of samples increased as a function of linear energy density. And we saw that, for example, for low laser energy density, we can get microstructures having lack of fusion porosities. So this is due to the less linear energy density which you are giving. And if we increase the laser energy density, we tend to decrease the lack of fusion porosities. We achieve good relative density up to 98.5%, but we still have cracks present in the microstructure. So all the stable conditions led to cracking. But there was a particular trend what we observed in the cracking. The mean cracking density measured from the microstructure decreased as a function of linear energy density. Okay, so now one can say that since we give increasing linear energy density, you can decrease the cracking tendency. So why not giving more energy to the sample? So let me remind you, in the previous slide, I have said that if we give sufficient energy, we can end up also getting unstability conditions. So the optimized parameter here corresponds to the parameter where we found the maximum relative density, but still cracks were produced. So moving into the cracking pattern, how is the cracking pattern and what is its mechanism? So to first identify where does the cracking occur based on the microstructure. So we choose the sample which was optimized, which was least in cracking, and we analyzed its EBSD microstructure along the building direction. And we clearly see that cracks are present in the microstructure along the building direction. And those are specifically also along the grain boundaries. So if we look at these statistics of grain boundaries, for example, based on its misorientation, so what it gives us. So for example, the low angle grain boundaries, which are less than 15 degrees of misorientation, were consistently non-cracking. But if we look at high angle grain boundaries, for instance, the dark bars here, those are cracked grain boundaries. So most of all the grain boundaries were high angle grain boundaries. But there are also few high angle grain boundaries which were non-cracking in nature. So to identify why is this high angle grain boundary non-cracking, we thought, okay, let's have a look at relation of cracking with respect to the melt pools. So we clearly see that cracking is along the center of melt pool. And this explains why certain high angle grain boundaries which are located away from the melt pool, which are not localized in the center, can be non-cracking. So cracking is intergranular in nature, occurring along high angle grain boundaries and exactly at the center of melt pools. Now let's see when does cracking occur. So to do that, we did fracture surface analysis. So basically, we did a tensile experiment on the cubes perpendicular to the building direction. So the aim was just to identify the fracture morphology. So with the fracture morphology, we can understand what is the origin of cracking. For example, here you see that you have cellular dendritic arms growing, and we see a bit of initiation of secondary dendrite arms, but those are still in its initiation phase. So this clearly indicates that cracking is due to the liquid films trapped in the dendrites. So now cracking due to liquid film can be due to solidification or liquefaction. So solidification can occur during the last stage of solidification, or liquefaction can be due to the remelted melt pools, for example. So to solve this last ambiguity, we looked at the final melt pool, the topmost melt pool regions which are not remelted. So if we see cracks in that, for example, we clearly see that cracks in the last melt pool are occurring, and this clearly suggests that cracking is due to solidification and occurring due to the solidification cracking. Okay, now we have identified where cracking occurs along high angle grain boundaries, center of melt pool. We have also identified the cracking mechanism. So now let's rationalize this observation based on different hot cracking models. So basically the objective is to explain our experimental observations and to justify why cracking is occurring in such particular way. So to do that, let's have a notion about what is solidification cracking and its occurrences of different occurrences of events. So for example, if we see the solid in the blue color here and the liquid in the violet color, and as a function of along the thermal gradient direction, our solids will grow. So solids will grow along the thermal gradient direction. For example, you see the dendrites are growing. So at a particular stage, we will reach a first stage, for example, where you will have high liquid permeability, which basically means that the liquid will be easily entered into the dendrites and can compensate for the shrinkage and deformation. And most of the alloy, they have this issue with the shrinkage because the density of solid is greater than the density of liquid. So you have this shrinkage and deformation issues as well. So if you continue the solidification, you reach a particular stage where dendrites starts to get connected to each other. And this is a point where we can say the coherency point, and where liquid film starts to form. Now, further continuing the solidification, we can see the third stage where the liquid films are continuous in nature. And since they are continuous in nature, the mechanical resistance to this liquid films is very less. So this is the most sensitive region of the dendrite morphology where solidification cracking can occur. So to summarize these occurrences of event as a function of solid fraction, for instance, for low solid fraction, we have easy feeding of liquid, so no feeding problem of liquid. The second region can be identified like before the dendrite starts to coalesce. For example, after the coalescence point, we can have a big, good transmission of this, the mechanical strains to the neighboring dendrites. So before the coalescence, it's most critical to be cracking, for example. And after coalescence, you are a more resistant mushy zone. So the solidification cracking occurs in a critical region. So now moving further, we thought, okay, let's use a very predominant model, the Rapaz-Droese and Gremot hot cracking model, to understand the initiation of cracking, for example. So when two dendrites are growing along the thermal gradients, in the RDG model, they try to understand what is the pressure drop in the mushy zone as a function of the distance. For example, the pressure in liquid starts to decrease and reaches a particular cavitation pressure, which once it reaches this cavitation pressure, you nucleate a cavity, and this leads to cracking. And this decrease in pressure drop is due to the aspects of shrinkage and deformation. So higher the pressure drop, higher will be the cracking tendency. So if we look at how we estimate this pressure drop, here it's a big complicated equation, but in a minute I will just simplify it for you. For example, based on different materials parameter like shrinkage factor, viscosity, the solid fraction as a function of temperature. So these are material aspect of the model. The process aspect, for example, the thermal gradients and solidification velocities. There are microstructural aspect, for example, the coalescence temperature, the lower bound of the integral. So at what temperature the dendrite starts to coalesce. And there are other factors which are based on microstructures and processing aspect as well. For example, the primary dendrite arms and the strain rates. So now, okay, we thought, okay, let's use this model and try to identify different inputs needed to run the model. So the first input is the material parameter, which is solid fraction as a function of temperature. So we relied here on to estimate this parameter based on the Scheil-Gulliver model. So we thought like this could be a better representative of the L-PBF process, since the diffusion in solid is neglected and there is infinite diffusion into the liquid. So compared to equilibrium, we thought, okay, let's choose Scheil-Gulliver and define it as solid fraction as a function of temperature. The second input parameter is the microstructure aspect. So we have seen in our experiments that high angle grain boundaries were cracking. So can we include somehow the misorientation aspect into the model? So the way to do that is by modifying the lower bound, which is the coalescence temperature. And if we are able to identify this temperature as a function of misorientation, we can take that into account. The last aspect is the L-PBF process parameter. So for this, we relied on simple Rosenthal analytical solutions to get a notion of thermal gradients and solidification velocities. Okay, so now let's start coalescence undercooling. Why, how we can take that into account. So to define here, what are how low angle grain boundaries, for example, low angle grain boundaries can be attractive grain boundaries. So for example, as soon as these grain boundaries are in the vicinity of each other, this coalesce. And for example, there will be high angle grain boundaries which are repulsive in nature. So they need further coalescence undercooling in order to coalesce. So this undercooling in coalescence, according to the coalescence model of Rapaz, it is dependent on the grain boundary energy and the solid liquid interface energy. So if we, in order to estimate what is the coalescence undercooling, we need to have an idea of grain boundary energy and solid liquid interface energy. So let's start estimating the grain boundary energy as a function of misorientation. So in our modeling strategy, we relied on the literature which is based on the atomistic simulations for different tilt grain boundaries. So we thought, okay, let's take an average fitting of this grain boundary as energy as a function of misorientation and define it as the grain boundary energy as a function of misorientation. So if we see clearly that after 5 degrees of misorientation, we convert into the repulsive grain boundaries. And the curve attains a particular plateau for around 20 to 25 degrees of misorientation. Okay, now we have the grain boundary energy as a function of misorientation. So it's easy to calculate now the coalescence temperature as a function of misorientation angle. So here is a graph assuming the coalescence at solid fraction of 0.97. So how did we achieve this solid fraction of 0.97? In fact, we relied on the literature based on Guilhem ROUX's work. So basically they did the tensile test of a Mise zone and they found that the stress increases in the Mise zone after a particular solid fraction of 0.97. So they concluded that this is the coalescence solid fraction of the 6061 aluminum alloy. So we use this value in our L-PBF condition, assuming that in L-PBF condition, we might not have a change of coalescence solid fraction. So that's why we use this particular solid fraction value. So based on 0 to 5 degrees, the attractive grain boundaries, we know that those are non-cracking in nature. So, and once the repulsive grain boundaries comes into picture after 5 degrees of misorientation, the undercooling, coalescence undercooling starts to develop. So it decreases until a point, for example, at 15 degrees, we know that our repulsive grain boundaries will be crack sensitive. So at 15 degrees of misorientation, which is the critical coalescence temperature, can be estimated. So we estimated it around 395 degrees Celsius for our alloy for a particular misorientation at 15 degrees and for a coalescence solid fraction of 0.97. Okay, now the another part of the puzzle is identifying the solidification parameters. So we chose the optimized parameters and we use the Rosenthal analytical solution to get an idea of thermal gradients and solidification velocities. So here is the building direction thermal gradient map of, for example, the laser is moving along the x-axis on the right side, and using the horizontal model, we can identify the thermal gradients. So here there are different curves. For example, the red contour indicates the liquidus temperature. The green contour indicates the coalescence temperature at solid fraction of 0.97. The black contour indicates the temperature of solidus. So we estimated the thermal gradients along the coalescence solid fraction. So as a function of melt pool depth, for example, the thermal gradients here, we clearly see that we increase the thermal gradient as we go into the depth. So lower in the melt pool, we have higher thermal gradients, and above we have low thermal gradients. But if you look at the solidification velocities, it is completely different in nature. So it is inverse in nature. So at the bottom, you have low solidification velocity, and at the top, you have high solidification velocities. So these parameters are varying inside the melt pool. So we thought, okay, for a given laser power and laser speed, let's just take the average values along the melt pools and use this into the model. So this is how we obtained the thermal gradients and solidification velocities. So now to address finally why high angle grain boundaries were cracking. So based on our different inputs, the material, the microstructure, the L-PBF process parameters, we were finally able to estimate the pressure drop as a function of Mise orientation angle. Again, here we chose the same solid fraction value of 0.97 for the sake of complexity. The total pressure drop here, we see that after a certain misorientation of 5 degrees, we see clearly a jump into the pressure drop. So this clearly suggests that the pressure drop, in other words, the cracking tendency is sensitive to high angle grain boundaries. So for example, we know that the repulsive grain boundaries from 5 to 15 degrees will not be cracking, because in our experiments, we have seen that it occurs only after 15. So we said, okay, at 15 degrees and corresponding to a solid fraction of 0.97, let's estimate the pressure drop. And this will be the critical pressure drop above which cracking will occur. So we estimated that to be around 2.5 gigapascals. So this is how we estimated, okay, cracking can be sensitive above this critical pressure drop. And pressure drop is also very sensitive to misorientation. So this is how we took into account the high angle grain boundary cracking. Now to identify why the central grain boundaries are cracking, we relied, okay, as we have seen in the equation of pressure drop, the integrals go from coalescence temperature to the liquidus. So if we look at the bounds of the these two temperatures, and within these bounds, what is the length of mesh zone? If we are able to quantify this on a microstructure level, we can have an idea about why cracking can be along the center lines. So here is the, just to give you a reminder about the top view EBSD image of our sample. So lasers are moving along X direction here, and we clearly see that the cracks follow the laser tracks. So if we look based on our horizontal simulation, the temperature fields along in the vicinity of where the laser is moving. So based on different contours, the liquidus and the coalescence contour here at 15 degrees, the white contour, we can estimate the length of mesh zone dividing by the thermal gradient for sure. So we clearly see that along the center line, we have high length of mesh zone. And this suggests that we might have higher pressure drops into that particular region. And this explains why we have a center line cracking in the topmost surface. Okay, now we have rationalized our cracking. Now let's assume, let's try and understand whether we can find some parameters which are less sensitive in cracking or not. So to do that, what we did, we took a range of laser powers and laser speeds, and we linked it to the thermal gradients and solidification velocities with our horizontal simulation. And we generated this hot cracking sensitivity map. So this map is basically in the y-axis, you have thermal gradient, x-axis, you have solidification velocities, and on the z, you have a pressure drop. So the black region here indicates the crack sensitive region based on our critical pressure drop of 2.5 gigapascals. So as you move away from this black region, you tend to be in a non-crack sensitive region, which basically gives you decreasing pressure drops here. Okay, so now this is the predicted, this is what our model suggests. But whether it is in line with our experimental observations or not. So to do that, we checked the crack density of the optimized sample and we superimposed into this HCS map. So we found that the crack density of 19 per millimeter square was just along the interface where you have transition from crack sensitive to non-cracking sensitive. If we look at other parameters which we studied, for example, we see an increasing in crack density as we move away from the interface. So the experimental points are qualitatively in agreement with what we have estimated with the HCS map. So one inference from this HCS map can be, okay, by decreasing the solidification velocities to 0.2 meters per second, we can be in the non-crack sensitive zone. So to achieve that, we need to be in the laser speeds of around 100 to 200 millimeters per second, which is quite low. So these are insights from the model. But practically speaking, these lower speeds can induce different problems like spattering and keyhole porosities, and there might be other technological issues. So in short, it's very difficult to achieve a crack-free specimen just by playing with laser powers and laser speeds. So now, okay, since it was not enough, just playing with powers and speed, we shifted our attention to preheating of powder bed, because in literature, it is reported to be mitigating cracking. So here is a microstructure where for a particular linear energy density, for our case, no preheating condition, we get cracking. But for a similar linear energy density with a preheating of 500 degrees Celsius, this is from the literature, we end up having non-cracking. So the difference, what we have observed is the primary dendrite arm spacing. For our case, we have around 0.06 microns, which we experimentally measured. But from the literature, this particular microstructure, it shows that the primary dendrite arm spacing is way bigger than what we observed. It is around 15 microns. So cracking mitigation is possible due to 500 degrees of preheating. And the main difference with what we observed is the primary dendrite arms in the two cases. So now the idea is, can the RDG model capture the beneficial effect of preheating or not? So to do that, we did changing of laser power speeds and the preheating temperatures to have an idea of thermal gradients and solidification velocities. So here is the similar particular curve, thermal gradient as a function of melt pool for no preheating conditions, the red one. And if we introduce the preheating temperatures of 500 degrees Celsius, we see clearly a decrease of several orders of magnitude of our thermal gradients. But let's see what solidification velocities gives. So for a no preheating, we have a decrease of, as a function of melt pool. But when we introduce the 500 degrees Celsius of preheating, our solidification velocities is not that much affected. The magnitude is not changing, although there is slight difference since melt pool dimensions might change due to preheating. So the thermal gradients are hugely affected without much an effect on solidification velocities. So now we implemented these parameters into the RDG model just to have, okay, let's see what the model is suggesting. So we generated the similar HCS maps for the no preheating condition on the left here. And on the right, we have a preheating conditions where the thermal gradients are hugely, largely decreased, and the taking into account the primary dendrite arm spacing as well. So we clearly see that the HCS map on the right for the preheating condition gives us low pressure drops. And this indicates that we have less crack sensitive microstructure. So the RDG model was able to capture the beneficial effect of preheating. But we know that these particular preheating conditions, for example, there are concerns in terms of the productivity. Since you are increasing the temperature, you are evaporating the volatile elements like magnesium, and there are difficulties related to installation. So in short, it can be also a bit tricky in order to implement preheating. So let's now change our attention towards what is the effect of solute content modification. But just to remind you, in my introduction, I said to you that I will be focusing on processing optimization. So now why I'm shifting. It's just to have an idea about how the model is giving us how we were able to rationalize based different solute strategies, which are already defined in literature. Since L-PBF process parameters were not able to mitigate cracking, we shifted our attention a bit. So we did several solute content modifications into the standard 6061 aluminum alloy. But here I will be presenting just a particular case, which is the zirconium addition. Zirconium addition is reported hugely in the literature to be cracking mitigating. So the idea is whether this solute content modification can be captured, the mitigations with zirconium can be captured by the RDG model or not. So to do that, we just change the solid fraction, the solidification path of the alloy, and assuming the rest of the metallurgical parameters are kept constant. So we end up getting a pressure drop, for example, as a function of zirconium addition, different zirconium additions. So for the standard 6061 aluminum alloy, we were at 2.5 gigapascals of pressure drop. And after we increase the zirconium additions, we clearly see that the pressure is increasing rapidly. We end up getting high crack sensitivity with zirconium addition. This is contrary to what is presented in literature. So to identify what is lacking in the model, we thought, okay, let's check the microstructure of the zirconium modified 6061 aluminum alloy. So the microstructure is quite complex here. For example, compared to our standard 6061 aluminum alloy, we clearly see that it's a duplex microstructure with columnar grains, the long elongated grains here, and the equiax grains are present simultaneously in the microstructure. So it is quite different compared to our standard 6061 aluminum alloy. So this is the reason probably that the RDG model was not able to consider the grain refinement, which is introduced by the zirconium. So probably this is the reason why we were not able to capture the beneficial effect of zirconium into the 6061 aluminum alloy. So, okay, we have studied processing optimization. We have studied a bit of solute content modifications. So now based on all the study, let me present you the final conclusions of the work. So based on the experimental characterizations of the 6061 aluminum alloy produced in L-PBF conditions, we observed that we concluded that it is highly challenging to fully prevent cracks by just playing with the first order of process parameters. We know that cracking occurs particularly at high angle grain boundaries and exactly in the center of melt pools. Cracking also had a particular mechanism, which is the solidification cracking, occurring in the last stage of solidification. Based on our modeling work of the crack initiation, thanks to the RDG model coupled with the coalescence theory and the Rosenthal simulations, we were able to estimate a particular critical pressure drop, which is around 2.5 gigapascal, above which a cracking is quite sensitive. We also identified which are the processing parameters which are key to reducing this pressure drop. For example, we need to go in low laser speeds. We need to implement high preheating temperatures, for instance. In our study, we also identified key metallurgical parameters. For example, the coalescence solid fraction, the primary dendrite arm spacing, the misorientation aspect of the microstructure, the viscosity, the solid liquid interface energy. So these are the parameters which we have identified. So now let's see what future perspectives can we think of. For example, based on, we have identified three different perspectives, three different directions in which we can go. The first one is the processing aspect. The second one is the alloy designing aspect, which metallurgical parameters which we need to consider. The third will be the improvement to the modeling strategy, how we can implement different aspects and improve the model. So the first one is the processing way. So we know that by managing and controlling the cooling rate, we can clearly control the primary dendrite arm spacing, for example. And this can be controlled by, this can be done by implementing preheatings, for instance, and implementing the twin lasers as well. So if we are able to put two different lasers into the machine, one which is just preheating the powder and another which is just melting, in this way, we can have a control of cooling rate, and we can have a direct implication on primary dendrite arm spacing. And this might change the cracking tendency. Another possible aspect could be the studying the effect of scan strategy, for example. This we didn't study into in detail into our work, but this can be also possible because changing this scanning strategy between two different layers can modify the local parameters and have an effect on cracking tendency. The second aspect of the work could be thought could be thought by alloy designing aspect. With different metallurgical parameters. For example, the most important parameter which we have identified in the study is the coalescence solid fraction. Based on our sensitivity analysis to pressure drop, for example, just by changing the coalescence solid fraction, we change the pressure drop to different orders of magnitude. For example, going from 0.9 coalescence solid fraction to 0.97, we have huge increase of pressure drops. So lower coalescence solid fraction will give us less sensitive to cracking, and high coalescence solid fraction will give you high sensitivity to cracking. So this sensitivity was also true if we go from 0.98 coalescence solid fraction to 0.99 as well. So just by changing little bit the coalescence solid fraction, you have huge difference of pressure drop. And to achieve a low coalescence solid fraction, we can think, okay, we have found in literature that magnesium is a element which can have an effect on coalescence solid fraction. With magnesium addition, we can decrease the coalescence solid fraction. The second interesting parameter is the solid liquid interface energy. We know that this parameter is able to control the coalescence undercooling, and this is how it can affect the cracking occurring at high angle grain boundaries. So these, for example, it is reported in literature that solid liquid interface energy can have an effect on the growing dendrites, like it can have an effect on the anisotropy of the growing dendrites and change its particular orientation. For example, zinc is reported to have an effect on the solid liquid interface energy. So further research efforts are needed to take that into account and identify which elements can control solid liquid interface energy. The last parameter can be thought of is the viscosity of the liquid. For example, we know that viscosity can be temperature dependent and also solute content dependent. So, and it is very tricky to understand which viscosity is needed to achieve a crack resistant microstructure. So and in terms of binary phase diagram, for example, it's very easy to do experiments to estimate the viscosity of liquid. But when you have a composition which is complex like 6061 alloy, which has so many elements, you need to study what is the effect of each element on the final net viscosity. So there is scope of improvement in order to have a better understanding of viscosity of the 6061 aluminum alloy. For example, we can have a look on silicon and zinc, which are reported in literature to be decreasing the viscosity. The third aspect of the perspective of the study could be the improvement in the modeling strategy. For example, we know that the RDG model was not able to capture the grain size, and how we can do that, taking into account the grain size into the model. So for example, if we have a refined grain structure, we can distribute the strains which are felt by the growing dendrites into different interfaces, into more interfaces, for example. And this is how we will decrease the net strain rates which are felt by the growing dendrites. Another way is like having a better prediction of microstructures. So since we were, in our modeling criteria, we never predicted microstructures. So if we have a better prediction of microstructure and implement the RDG criteria simultaneously, we can have a better notion of predicting cracking. So to do that, predicting microstructure, we can think of doing several finite element simulations based on the local thermal and mechanical fields at really small mesoscales, taking into account the L-PBF processing parameters. And by combining this with the the microstructural models using cellular automaton models, for example, this is how we can probably predict the microstructure in L-PBF for a given composition. We can also, we can use these predicted microstructures and collaborate it with the RDG model to finally estimate the pressure drops which are in the intergranular regions of the material. For example, using different fluid flow models, we can have an estimation of what are the pressures needed to achieve a critical point after which you might have cracking. So pressure drops can be calculated within the grain boundary network using different fluid flow models. And in this way, we could have a better estimation of our cracking tendency if we are able to predict microstructure. For example, if we use this particular methodology, we might, I'm not sure, but probably we might can predict the beneficial effect of zirconium into since it is refining our microstructure. And this is how we can predict in a better way. So that was up for my perspectives points, and thank you for your attention, everyone.
Thank you, Akash, for this very clear presentation. I really liked it.
Merci beaucoup.
It was very nice to follow, and it made a good summary of the huge amount of work you've done. So now let's go for the first examiner, Aude SIMAR.
Yes, hello, do you hear me well?
Yeah, we can hear you.
Yeah. Okay, well, congratulations, Akash, for this nice presentation, of course, for the nice work, but that I have already said in my report. So it was really nice to see a fundamental analysis of the hot tearing, because you often see people mentioning hot tearing and well, haven't confirmed anything. And I think that was nice to have this analysis and the quite fundamental aspect of it. Mm-hmm. So the experiments were nice, and of course the model interesting and these maps that you developed were interesting. I do have a few questions for you. Some of them I mentioned in my report, and maybe will not be discussed today as for a matter of time. Mm-hmm. So let's go for my first question that concerns page 84 of the manuscript.
Yeah.
I don't know if you have one around.
Yeah.
It'll be easier for you to, well, maybe go back to the figure, but basically it's concerning the selected scanning strategy. Yeah? So you're selecting a scanning strategy without any rotation between successive layers.
Yeah.
Can that influence the cracking? You mentioned that as a perspective also in your slides there.
Yeah. Yeah.
Can you tell me a bit about what's your feeling that would be the best solution for avoiding hot cracking in terms of a scanning strategy? I'm not so convinced that there you selected the best scanning strategy to limit this effect.
Yeah, thank you for your question. Yeah, in fact, when we started this work, we decided, okay, because in literature there are several different strategies which are mostly renowned. For example, changing between different layers using an angle of 67 degrees, for example. These are strategies which can produce dense microstructures. But you know, when we try to complexify different strategies between two layers, it might be difficult to have an interpretation of the microstructures. So in order to have a simple scanning strategy without having any rotation aspect into picture, we thought, okay, let's choose a simple strategy without having rotation aspect. And in this way, we can have an effect, and we can clearly look where the cracks are located with respect to the melt pools. How is the cracking in terms of the simple microstructure? But for sure, I agree with you that changing scanning strategy can have an effect onto the tendency of cracking where you are looking exactly. For example, we tried to, in our 2D experiments with the bulk substrates, we tried to change a bit of the hatch spacing, and we found that cracking was still existing even if we reduce the hatch spacing, and we found that the cracking was moving along the directions where lasers are passing continuously. So this is also probably an indication where that probably changing the scanning strategy will have an effect. But true, we don't have real elements to conclude based on that aspect. And that's why I've mentioned that in the perspective aspect of the study, we need to look into that in more details.
Mm-hmm. I thought it somehow makes sense in terms of fundamental analysis.
Yes.
It would be nice to see if there is an effect on grain orientation, even though it's
yeah, in literature, they have
people show the same results as you when they're using different scan strategies. So I'm not fully convinced it will solve the problem.
Mm-hmm.
Let's move to page 109, where you have these HEADF EDX maps. So my question is, what could be the effect of this irregular precipitation at grain boundary that was revealed by this HEADF maps? I understand you could need to confirm such an effect, but maybe this is an interesting observation or even a track for improving the problem of cracking.
Yeah, in fact, the goal was to identify whether we have a really effect of the particular grain boundary which we are looking into this aspect. For example, whether there are particular elements which are segregating along the grain boundaries. But so to identify this, we selected two grain boundaries. One is cracking and one is not cracking. So both the grain boundaries were high angle in nature, for instance, but we observed a slight difference into the precipitation aspect of the different elements along the grain boundaries. But in order to conclude that, okay, this particular cracked grain boundary, which is high angle in nature, it is giving some particular continuous precipitation of elements along the grain boundaries compared to the non-cracking grain boundary. So in order to really understand this misorientation based precipitation of elements, we might need to do advanced analysis, for example, A-star analysis based on the local misorientation at nanometric scale levels. And we might also need a lot of statistics, because here in our study, we only selected two grain boundaries, for instance, to have this analysis. But yeah, it is promising, the first results. But I agree that we might need further insights into this observation based on different, with statistics for sure.
Mm-hmm. Yeah, but I think it's really an interesting result, and I haven't seen that in other places. For the 6061, you often see these kind of things on 7000 series alloys, but not so much on 6000 series, even though we can have observations of grain boundary precipitation and precipitate free zones associated. But well, that could somehow affect us, and I think it's an interesting thing to pursue and go maybe then for a publication on this topic, because that could influence significantly the work.
Yeah, I agree that, based on our thermodynamic simulations with the Scheil-Gulliver model as well, we found that certain elements, they have low partition coefficient, for example, depending on different elements we have selected. So we found that certain elements might have different partition coefficient, and this might lead to segregation along the grain boundaries, selective segregation along the grain boundaries. But to confirm this, we might need a star or even the tomography, for instance,
Do you think you
atom
can
probe tomography, to really quantitatively measure the segregation aspect.
Yeah, okay. Atom probe tomography, I agree, but tomography, not.
Yeah, atom probe tomography, I meant, yeah.
Well, maybe holotomography could reveal that the advantage would be the statistics, but
Yeah, for sure.
yeah. Can you, just a quite general question, can you confirm me that the very fast solidification conditions typical of laser powder bed fusion can be well treated by classical solidification cracking models, such as the RDG model that you were using?
If I well understood your question, like whether the solidification conditions of L-PBF can be treated by RDG model or not.
Yeah. Well, is the RDG model capable of, well, treating fast solidification?
Yeah, in fact, the origins of the RDG model is based on the initiation of cracking along the two dendrites, for example. So as we have shown in our microstructures with the fracture surface morphology, we have dendritic morphology. So based on this solidification mechanism occurring along the dendrites, we can use the RDG model. Okay, but in the RDG model, we have different thermal gradients and solidification velocities. So it is, as long as we are able to estimate these thermal gradients and solidification velocities for a given dendrite, doesn't matter in which process, casting, welding, or even in L-PBF, we can use the model in different processing conditions. I hope this was clear to you.
Yeah. Well, I would tend to agree, but I was having this thought about the validity, but your argument is basically that the mechanism is identical, and so you don't expect this to change the conditions. But I'm sure that Jean-Marie DREZET will have a thought about that, and we'll discuss that with you after. Well, in your model, what do you consider as the less reliable hypothesis, and how could you remedy to this if you had, let's say, endless time and if you had endless time and less experimental resources?
Yeah, it's a very good question. Basically, in order to have a self-realization of what my model can do and what it cannot do. So yeah, to answer this question, you know, we have a model in which we have used several assumptions. Right from the starting, for example, estimating the grain boundary energy as a function of misorientation. We relied on the literature based on the pure aluminium, which is giving such particular behavior of grain boundary energy. For sure, we can have this changing of grain boundary energy based on the composition aspect as well. So for 6061 aluminum alloy, we might expect to have a change in grain boundary energy as a function of misorientation. So this was an assumption which we relied. So for sure, if I had some more time, we could go further into estimating that. Second aspect I was thinking is the viscosity of the aluminum alloy. It's very difficult. We relied also on the pure aluminum case to have an estimation of 6061 aluminum alloy viscosity. Yeah, future there might be a work needed to be done in that aspect as well. Third point I can mention is the estimation of coalescence solid fraction, for instance. In our entire work, we relied on the work of Iliane Giroux, which is basically during the welding. So in the welding, she did tensile experiments in the Machi zone for a very low solid cooling rate, for instance, 80 Kelvin per second. which is far away from what is the cooling rate introduced into the L-PBF. L-PBF, we have around 10⁶ Kelvin per second. So this is a very strong assumption that based on the cooling rate, we thought, okay, the coalescence solid fraction might not change. So in order to estimate the real coalescence solid fraction of the alloy in L-PBF condition, we might need several experiments really high to attain that cooling rate and do tensile experiments in that cooling rate. So it's very challenging to do. So yeah, there are these aspects, and also another aspect I can think of is the Rosenthal analytical solution model which we used. In fact, the model we selected just to have a rough estimations of solidification conditions in L-PBF, but to have a real estimation, we might need based on the mechanical aspects as well of the process to estimate it in the local zones at mesoscales. We might need finite element models to have a better predictability.
What do you call the mechanical aspects?
Like, for example, like compared to casting or welding, your microstructure, your metal is constrained by different bounds. Here in L-PBF, we don't have those bounds. So in that, we can have a difference. So yeah, this is what I meant by mechanical bounds.
Yeah, I think it's more, well, yes, that makes sense. Okay. You mean that you would consider the residual stresses or
they might have an effect as well, because
that would play on yeah, but you can't introduce that so much in, yeah, well, yeah, makes sense in a way. Yeah, probably a finite element model might be more interesting now.
Yeah,
even a thermal model because of the imprecisions here and the hypothesis of the Rosenthal model.
Yeah, I agree that in our modeling way we have done several assumptions to take into account different aspects of the work. For example, the coalescence undercooling, which we estimated, we relied on the coalescence theory of Rapaz, Professor Rapaz. So we estimated that for a 15 degrees of misorientation, we might have a coalescence which is way below around 395 degrees Celsius, for example. And to estimate this experimentally, to prove this, okay, this is a reliable value, we are not sure in this way that it is really existing, it is really taking place actually at that particular coalescence.
Okay, we might move to another question. Your estimated pressure drop with the RDG model sounds very large compared to literature, and you're attributing that to the specificities of the L-PBF process.
Yeah.
Can you explain to me a bit what you meant by that?
Yeah, in fact, I meant in this way because most of the pressure drops which are reported in literature, those are specifically applied to welding conditions. And in welding conditions, you have way lower thermal gradients, and even the mechanical, the strain rates are quite less compared to what we have found. For example, the strain rates which are mostly reported in literature are like 10⁻⁵ per seconds. And here we came up with a empirical solution to estimate a strain rate which is several orders of magnitude more than the strain rates in the welding conditions. So based on these particular points, for example, the thermal gradients, the strain rates, which we have estimated specifically for L-PBF, this makes the pressure drop go so high into in its value. And also the fact that we have included the coalescence undercooling into the model. This changes the lower bound of the integral of the RDG model, which further makes the pressure drop increase. So, these all factors make the pressure drop to attain that particular value of gigapascals.
Yeah, I was wondering if this solid fraction and the 97% that you're using, maybe that one is one that is, well, it's strain rate dependent, and I don't know. It's an open question, but maybe the fast solidification play on that aspect. Just a very final question that's related to your perspectives as well. You're mentioning this cellular automaton solution to account for the effect of the grain refiner on the model, and that you're not capturing with your model. Can you tell me a bit more about this? Because you said a bit in the in your presentation about this, but this is still quite nebulous for me.
Yeah, true that. In fact, we haven't really worked on the cellular automaton model in order to predict the microstructures. It was just a thought that, okay, if we are able to predict reliably microstructures, for example, with zirconium addition, we can estimate a microstructure based on L-PBF conditions. We can have a reliable criteria, and if we collaborate the RDG model into the cellular automaton model, for example, and estimates the real pressure drops moving which are along the grain boundaries, for instance. So in my idea, I have not much details about it, to be honest, about this cellular automaton model.
So if I understand correctly what you're saying, the cellular would be a cell would be a grain.
Yeah.
Right.
So yeah, basically, when we are introducing a grain size aspect into the RDG model, we will look at, instead of dendrites, how they are coalescing, we can look into how the grains are coalescing. So we can update a model in this way that how the grains are coalescing at a particular instance as a function of temperature, for instance. And does this grain refinement have an effect on this coalescence aspect or not? So in this way, if the liquid is able to move easily into between the two grains, and this way we can have an idea about the pressure drops.
Yeah, what you were showing in your schematic was more to me looking like a composite model, but yeah, anyway, it doesn't matter how you call it. The principle is you're sharing the strain among different locations. Okay, I think my time is up. Thank you again, and hopefully I can meet you in person one day.
Yeah, I would like it. It will be a pleasure to meet you. Yeah, thank you very much for your questions. Yeah.
Okay, thank you very much, Aude. And now we are very lucky to have the D of the RDG model.
Yes.
So I guess you'll be able to
Alexis.
comment on the applicability of his model. So please, Jean-Marie, it's your turn.
Yes. Thank you, Alexis. Can you hear me? Yeah, that's fine. Aude, yeah. Okay.
Everyone?
Yes, we hear you.
Yes, that's the T of the RDG, yes. So, okay, so Aude said already many things on this PhD work, and I have to approve her on the quality of this work. It's been a real pleasure for me to read this PhD work because it's the natural evolution of this RDG model that has been developed more than 20 years ago now. And I think you have shown really the limits of the model, like any model has some limits, and what could be the perspectives to improve it. Especially in terms of grain coalescence, that's a real issue.
Yes.
I really appreciated also the fact that you showed that some liquid film can survive down to 400 degrees. It's the order of magnitude, okay, but it's really below the classic solidus temperature, and those are really the detrimental aspect of the whole structure, solid and liquids, because the liquid cannot sustain any tensile stresses and deformation. Yeah, I really appreciated this. Thank you. And yeah, also the aspect of what could be improved, you know, in terms of grain structure, grain refiners, and surface active elements. I think these are the major three aspects that could help us also to fabricate acceptable pieces, you know, with no such defects. Okay, can you go to slide 14 and 15 when you? I'm going to, you know, to discuss with you on liquation cracking and solidification cracking.
Okay. This one? This
yes,
slide?
this one and the next one, but let's take this one.
Okay.
I think your argument of saying these are solidification cracking is based on propagation and not on initiation, because the cracks was already here, so there's no reason why it should not continue. You see my point of view? In other words, can you explain the difference between initiation conditions and propagation conditions?
Yeah.
That's very important when people study cracks, any kinds of cracks.
Yeah, thank you. It's a pleasure to have you in my jury here. First of all, thanks for being here. Yeah, it's a bit difficult question to address for sure.
Yes, for sure. Sorry for that.
No issues. No, in fact, it is true that the RDG model is, we are looking really into the aspects of initiation of cracking and not the propagation aspect. For me, the initiation point, as you mentioned, that once we reach a particular cavitation pressure, we have a nucleation of void, which leads to the initiation of cracking. This is the starting point of initiation. And for me, the propagation can be due to several different aspects. For example, if we have, for example, two dendrites are growing in a particular way, if the space between the interdendritic region it's more than the liquid feeding, which is coming, which is not able to liquid fill between the two dendrites. So if this condition is maintained all the way, you might have a propagation of cracking. So this is further after the cavitation pressure has reached. So I think in this way, if we look at, because in our study, we never looked into the propagation aspect of the work of the cracks. It was all the time the cracking aspects. Even if we look at the Sindoku model, for example, in that model, he also says that, in fact, he looks clearly at the region between the grains, the grain boundary region. And when the two grains are growing towards each other, the region between that and the liquid which is feeding inside that particular grain, this can, if it increases, this can have an effect into the propagation of cracks. So if we look into that aspect, I agree that why not, as you pointed out this correctly, that why not once you have initiation, you have cracking all the way along. But just to show you that, okay, we found that cracking in the topmost layer was, which the melt pool, which was not remelted. So this was the melt pool, which was at the last stage of solidification, and we saw that cracking was there. So if we have a look at the fracture surface of the last melt pool, if we have dendritic morphology there, we can say that it was due to the liquid films. And this is, so in all our fractography, right from bottom to top, we had cellular dendritic arms which were growing. And probably this is the first indication that we have a particular solidification cracking. But I agree that probably we don't have all the elements to make a strong conclusion about it.
Yeah. Me neither, so don't worry.
So, but
what could be, I mean, do you see any difference between liquation cracking, because you mentioned this in your PhD work, and solidification cracking? What could be really the difference between the two of them? It's in between the grains, okay, both of them. Then the the broken surfaces are dendritic, okay? How could I say this was a liquefaction cracking and this was a solidification cracking?
Yeah, it's again a good question. Probably we could do further experiments just by remelting that laser, that particular region, and understanding, okay, if once we have remelting, whether the crack is present or not. And if cracking is present, probably we might have an understanding into that aspect.
In fact, I think the answer is in your PhD. You mentioned that the liquid films can survive down to 400 degrees.
Yes.
Then imagine a crack forms there. Then isn't it a liquefaction cracking?
Mm-hmm.
Or imagine it initiates in the heat affected zone, you know, far away from the liquid pool. So in other words, you know, it's an open discussion. It's just, for me, liquefaction cracking and solidification cracking, I think it's the same.
Okay.
At least when you have such a liquid pool and, you know, well, open discussion.
Yeah.
Don't worry for that.
Yeah,
you know, it's just to discuss. We are here to discuss.
For sure.
That doesn't change any things on the merit of your PhD work. Very nice PhD work. Okay. What kind of experiments could you imagine to show that liquid films can survive down to such low temperatures? Just, you know, open your mind and...
yeah,
not necessarily in L-PBF.
Not necessarily
yes.
L-PBF, yeah, true. Like, for example, it's a very good question because we are saying that liquid films are staying up to lower temperatures way below the solidus. And in a normal environment, if we do a particular test of tensile test as a function of temperature, after the solidus, you might not have any evidence of the liquid films. So probably we can have a look the stress states at very minute level between the dendrites, or how is it behaving. For example, doing in situ analysis or X-ray high-end technology, yes, advanced characterization.
Yeah, in situ solidification. And bi-crystal.
Yeah, for
only
example.
2 crystals, you know,
yes.
like the experiments on Anvang.
Yeah.
It's not that easy, but you know, with grain selectors, and imagine to have only 2 crystals and then try to follow what's in between. Yeah. Okay. Okay, so other little things, you know, that I mentioned in my report. I think you made a little mistake on the strain rate.
Yeah. I agree that it was a good point. Okay. I agree that it was a slight mistake, but
it is not going to change.
Yeah. We estimated that our pressure drop values based on this slight changing of replacing by G to GX. Yeah. It will have slight effect on the pressure drop, but
not so much.
Not so much, I think. Yeah.
By the way, the pressure drop, yes, Aude mentioned it. You find very huge values. You know, gigapascals, things like that. Don't you think that something will happen before reaching this cavitation pressure simply?
Yeah, for sure.
So in other words, one can see the pressure drop as a sensitivity to cracking. The higher this quantity, okay, physically it's a pressure drop. Yeah. But, you know, experimentally speaking, it's the higher this quantity, it's a hot cracking sensitivity.
Yeah.
Because imagine in that liquid films, you have whatever, plenty of solutes that, that can be rejected. You have other phases, I mean, new phases that might appear, metastable phases, we don't know, and pores as well, pore microporosity.
Microporosities, yeah, true.
Yeah. Okay, can you go to slide 20? Maybe I think it's easier to see on the slides. Yes. So delta T and the cooling, and that's clearly mentioned in your PhD work. That I really appreciate.
Yes.
Okay, it's a function of 2 quantities, the solid-liquid interface and the grain boundary energy. if you had to act on these quantities, which one could be the predominant one, and how would you act, you see, to decrease this delta T? Do you have any idea? You know, it's an open question.
Yeah, I agree. And it's quite an interesting question as well, because if we are able to control these quantities, we control the coalescence under cooling. And if we control the coalescence under cooling, we can control the liquid films not persisting up to lower temperatures, basically. So according to me, I have this feeling that the solid liquid interface energy, which is very important aspect into the coalescence theory, this is reported in few publications I have seen by Professor Rapaz, that he has tried to change the composition of aluminum alloy from with the help of zinc and some other elements. And he observed that there is a change in dendrite orientations, and this particular solid liquid interface energy is able to control the anisotropy of the dendrites, growing dendrites. And according to my feeling, this is what I think, but probably it might be not true. But if we identify such elements which show clearly that they can control this particular solid liquid interface energies, we might have a better control about the coalescence. I think so, compared to the grain boundary energy, which can change due to the misorientation for sure.
Yeah. Yes, the grain boundary energy is mainly a function of the angle, the misorientation, and maybe to a second order of the surface active element. But surface active element definitely will impact like viscosity as well. Viscosity will impact the solid liquid energy. It's like sulfur in steel. Like sodium, strontium. Of course, then you can restart a PhD work. I mean, you have all the periodic table to work on. Yeah. Almost.
Yeah, true.
Okay. Yeah. Bismuth, sodium, strontium, antimony.
I think that's why you mentioned all this. Why I didn't studied these elements. Yeah, probably.
No, you cannot do everything, but people are working on it, I think.
I see.
So that's the coalescence. The other aspect is grain structure.
True.
And if you go to slide 32, maybe you mentioned the strain localization. When you have epsilon dot divided by n, maybe further down. Yes, strain localization. So one way to reduce hot cracking, and it's well known, is to have a finer microstructure.
True.
Because each liquid film that might survive will support less strains. So in your process in L-PBF, could you imagine to have a finer microstructure?
Based on the changing of compositions, we have shown that if we add zirconium, we have a grain refinement. And we clearly show that you change the columnar grain width with the zirconium addition. So if we see that we have refinement due to such elements, we can peut-être I have muted everyone. Okay. So returning to the point, I think since if we have a smaller columnar grains which are growing, in this way we could identify that the strains acting over the entire region might be distributed into several interfaces. And this is what we think, that if we include this into the modeling aspect, we could take into account the grain size aspect. So this is what was your question?
Yeah, in the process, in other words, could you imagine to use grain refiners?
Yes, in fact, there are...
Even in the powder, by the way.
Yeah.
Of course, yeah.
Like, for example, there are...
and that's what happens with zirconium. In fact, zirconium, you have a duplex microstructure. You still have those columnar grains that are rather coarse and little equiax grains. The best would be to have everywhere small equiax grains.
True.
Yeah. So I think that, and that's in your PhD. The two major directions. Is surface active elements to play on the coalescence and grain structure. And of course, it's not in the RDG. RDG is a two-phase continuum description. You know, very simple. Consider delta P as a hot cracking sensitivity. The higher, okay. That's why we reach so high values, which is almost nonsense, maybe. You see, by the way, I come back on the, and I'm going to finish on this. Crack propagation and crack initiation. Imagine you have a crack in one, you replace a grain boundary by a crack. Yeah. Epsilon dot goes back to 0 on that liquid film. So you see, we have to be, it's not for you especially, it's for many people working on hot cracking. Propagation is not initiation.
True, true. Completely agree, yeah.
Propagation is not initiation. And why did we and also Sindoku concentrate on initiation? It's because we don't want them. We don't want them. So we start to study the initiation. Okay?
As long as we are able to control the initiation, we can control the propagation as well.
Yeah, but propagation is too late.
It's
unless you want cracks. If you want cracks, that's perfect. Okay, I'm too long now, Alexis. That's fine. Maybe one very last question. That is not. It's the most again a discussion. What could be the link between microporosity or porosity and cracking?
Yeah, it's also an aspect which needs to be really looked into, because in my PhD we also found that the cracks were, there were many instances where microporosities were inside the cracks, and probably due to the cracking during the propagation, the crack propagated along these microporosities. Or it is also possible that the crack nucleated at particular porosity. This is also possible. So in order to study this link, the porosity and the crack, probably we might need certain high in situ experiments, which I think recently they have published a link between, for the 6061 aluminum alloy, what is the link between microporosity and cracking. Okay. And they found that cracks are really, they are selectively initiated at these microporosities. Probably the maybe it is keyhole porosity or
so that comes back to the delta P.
That
is, you know, a defect will initiate or certainly initiate on a previously formed defect. And microporosity forms closer to the liquidus as soon as you know at higher solid liquid fraction, and then develops and so on. And last thing, I promise it's the last. Coalescence. Why should coalescence take place at a given solid fraction? It's a transition.
It is a transition. True. I agree.
See, I ask question and I give the answer.
No, in fact, what we think, it is true that coalescence is a transition aspect, but to my understanding, in order to detect coalescence, it's very tricky. But the experiments performed by Ilian Giroux, they were quite interesting, and I felt that it is the first time I found an experiments done to detect coalescence. And they found that this coalescence is not particular arbitrary range. At particular solid fraction, they clearly see that the stresses are increasing and the meshy zone, which is becoming much resistant. And that is the first indication for me that coalescence is taking place at a constant solid fraction. Theory, but in practical, it occurs from the coherency point. For example, the dendrites are starting to get connected, and then you have liquid films which are forming continuously. And at a moment when coalescence takes place, this liquid films get disintegrated into different smaller
pockets. Or,
exactly, pockets.
And it's a 3D effect.
3D effect, true.
Yeah. So, in fact, the worst liquid films are those who are continuous, you know, and yeah, it's a transition, definitely. Okay, again, thank you for this very nice piece of work. It's been a real pleasure because I saw written what could be the future, I mean, the natural evolution of this model.
I agree.
And it's written, and all the directions are there. So thank you so much.
Thank you very much for your questions. And
thank you.
It was a pleasure presenting in front of you, the creator of the model.
Thank you.
Okay, thank you. And I'm sure it will be the pleasure also to listen to Marc Thomas' questions.
Yeah, for sure.
So now, Marc Thomas.
Sir, your micro is off, I think. Just a second. Okay. Okay.
It's okay?
Yeah, sure. Thank you.
So I was very pleased to read your PhD work. Very interesting. I must confess that I was not so familiar with aluminum alloys, but I did work on nickel-based. I do work on nickel-based superalloys, and I can see strong similarities between these two families of alloys. So I'm not completely lost. So I was very impressed by the quality of the work, both experimental and numerical, and you are feeding very well both experimental and numerical aspects, discussing both. So that's a very nice PhD work for that. And about the manuscript, I noticed that it is very well written. I was waiting for the first fault, page 78. So, so very few faults. So that's very nice, nice manuscript. And also, I should mention that you can read that like a detective novel. Who is responsible for cracking? You see, so that's very interesting to read.
Thank you for your comments. Yeah.
So to start, I have two comments and very easy questions. The first comment was about you didn't mention at oral presentation, but at the beginning you had two powders, and you try to find one of them. And mentioned that maybe the powder 2 was not very good, didn't have a very good flowability because of the moisture. And I must say that I noticed that there was quite a big difference in powder size distribution between these two powders, and maybe the lower flowability of powder 2 maybe could be responsible from the size of the powders as well, not only on moisture.
True. I agree. Yeah, because the powder 2, which we have analyzed, it was a bit finer in nature. And since you have fine powder size distribution, probably you have a lot of cohesive energies which are acting, which are making the powders coalesce and stick to each other. And this can affect the flowability of the powder. So I agree with you that it might not be just the moisture content, and it is also the powder size distribution. Yeah, totally.
Yes. Fine. The second comment was about what Jean-Marie DREZET said about the solidification cracking and the equation cracking. That's right. It's very similar mechanisms, except maybe that the equation cracking happens from the remelting with the occurrence of liquid phase by remelting. And but I was a bit surprised from the literature that for welding, the equation cracking that was evidenced, and in your work you quite well evidenced that it was solidification cracking. So I would expect quite the reverse, maybe solidification cracking in by welding and maybe liquefaction cracking by L-PBF. So maybe this means that maybe there are not so big difference between these two mechanisms. And I don't know if you have a comment about that.
Yeah, I agree. As we discussed previously with Professor DREZET, that yeah, we need further elements to conclude on that aspect, that whether it is really the solidification mechanism that we have discovered into in our work. But yeah, in the welding literature, in the literature, for example, they have shown that it is it is possible also by solidification and liquefaction. So every time there was a bit of confusion that what is the actual mechanism that is making the 6061 aluminum alloy crack. So in our work, we just relied on the fracture morphology, the dendritic structure, and the topmost melt pool, which was thought to be not remelted. And we observed that cracks were present in that. So based on this, we concluded that it is solidification cracking. So
yes, it's very good conclusion. Yes, I agree. A question now is about you mentioned that for crack mitigation, we can refine the grain size in the mushy zone and to accommodate the strain rates. And for that, one of the possibilities, you didn't mention that at oral presentation, but in your thesis, you mentioned that we can use ultrasound.
Mm-hmm.
And you mentioned the work of Todaro.
Mm-hmm.
But that was with laser powder deposition.
Deposition, yeah.
L-PBF. What do you think about using ultrasound for L-PBF? Is it feasible for you? And is it something that could be interesting to?
Yeah, in fact, in my literature section, I have mentioned that a process methodology in order to achieve cracking grain refinement. There are researchers working in Australia. They have found that using ultrasound, you could break the movement of dendrites which are growing, and this is how you can germinate different grains on top of each other and get cracking grain refinement. Sorry. So yeah, in fact, it is not yet tested on aluminum alloys in L-PBF conditions, but to my feeling, yes, we could try, and probably this can be the only process way I can think of to achieve grain refinement. So yeah, it could be a possible solution, but there are much efforts needed to implement the frequency at which the ultrasounds are needed to be embedded into the machine. For example, there needs to be a study at which frequency you have complete grain refinement and not partial grain refinement. So
that's right.
So it's true that we need this aspect to be studied.
Good, good. Another point completely different is about magnesium evaporation. I don't have any information about what is the extent of this magnesium evaporation in the 6061 alloy. Did you make some chemical analysis in some after processing to?
Yeah, in fact, post fabrication, we did an ECP analysis of our cubes, that what is the actual composition of the of the microscope of the fabricated cubes, and we saw that there is a bit of magnesium which is evaporated around, and the evaporation was not so much. We had the compositions were in the range of standard 6061 composition, but I agree. I admit that we have seen a bit of magnesium evaporation.
A bit of magnesium evaporation.
Around 3 to 4% of max 5%. This is what I remember, if I remember well. in terms of 8% of the magnesium.
Okay, okay, yes.
Compared to the initial powder composition.
Okay, okay. And not so big difference between the processing conditions?
No, this we haven't studied into detail. We only analyze the optimized sample for the CP analysis. We didn't study that is there any effect of processing parameters on the magnesium evaporation.
Okay, thank you. So I will finish with a question about your perspective.
Mm-hmm.
You mentioned different points in your perspective, process, alloy design, model improvement. What would be the best route if you want to develop not 3D cubes, but larger parts? For instance, if you have the objective of fabricating a 500 millimeter part, what would be the priority in terms of processing alloy and modeling?
True, it's a very important question and quite good question because it gives how we prioritize our future perspectives. So according to me, I think since in my study, I in a way concluded that processing optimization was not the best strategy in which we need to avoid cracking. And there are several issues. For example, I said about preheating that it's not very feasible to be implemented into the L-PBF machines. So the most prioritized perspectives of my study, I think we need to focus on the alloy development aspects. For example, we have shown that the coalescence solid fraction is very sensitive to cracking. And if we are able to control this coalescence solid fraction and basically controlling this metallurgical parameter of the alloy, we can have a better crack resistant microstructures. And this can be true not only for 6061. If we are able to control this metallurgical parameter, it can be true for other crack sensitive alloys, for example. So this is a way in which I think I would prioritize. The first is, according to me, going into controlling alloy development parameters. And the second aspect could be thinking out of the box in terms of processing, how we can control the cooling rates, for example, whether just by controlling the cooling rate, probably using twin lasers, we can have a larger dendritic arms, larger dendritic arm spacing, which is able to accommodate the liquid into the dendrites so that you have less cracking. So I think controlling cooling rate in L-PBF can be also thought as a perspective. So I would prioritize second into my list. The third one can be given that we have a particular composition and we need to identify whether it is crack sensitive or not. We also need to have a understanding about what microstructures it will give in L-PBF conditions. And for a given composition, we might need to have a good prediction of microstructure. So predicting microstructure, coupling with the RDG model and having a sense of whether this alloy will crack or not. I think this way can also be useful in identifying the perspectives of the study. So these are my priority order according to me. This is what I feel, and probably there are other ways which can be true. But so yeah, these are my thoughts about it. Yeah,
that's very interesting. Thank you very much, Akash, for your answers.
Yeah.
To finish, I must congratulate you again for all your work, and thank you.
Thank you very much. Thanks for your questions. It was a pleasure.
Okay, thanks a lot. Now, before going to the supervisors of this work, I will ask very, very short questions because we've had a long question session already.
Mm-hmm.
And also, I'm not very familiar with neither the solidification cracking. I did work on that a long time ago, but not since many years, and neither with additive manufacturing. So it will be probably quite naive questions. First, yeah, one of my questions was about this famous pressure drop, but now it's been discussed quite a lot. And effectively, I would say it's probably putting the dust under the carpet, this value. And I was wondering, among all the different hypotheses of that are behind this calculation, which ones do you think are the least valid? And I will cite 3 of them. First, it's been also cited by Aude first, is the effect of precipitation at the grain boundaries. Your very, very nice TEM experiments show that you have a very high fraction of precipitation at the grain boundaries. And then how do you think it's really valid to consider the surface energy of between 2 grains when 50% of it is covered by precipitates, which have their own interfacial energy, solid, liquid, and so on. And also, of course, the stress that can be supported by this grain boundary is affected by the precipitation on it. And so that would be my first comment. And related to that, do you think, you see that a lot of these precipitates contain iron, and iron probably has only a small effect on the solidification condition. Do you think it would be possible to study a 6061 alloy free of iron and to see if you have a big effect?
Okay, thank you. Yeah, those are quite interesting and difficult questions as well to address, I must admit. In fact, according to my feeling, yeah, I agree that we clearly see that there are a lot of precipitations along the grain boundaries, and controlling the solid liquid interface energy, you might need to take into account individual aspects of these precipitates linked to the actual alloy composition. So I agree with that. We need to, but we also need to study at what are the kinetics of this precipitation, for example, at what time they are forming, whether the precipitates have already formed before the cracking, or is it after the cracking when these precipitates are really taken into account. So I think the kinetics of this precipitation needs to be studied in detail. This we haven't done into our study, but this might need attention in order to understand its interaction well in a proper way.
I guess so. The second point would be the effect of strain relaxation. When you said that between traditional solidification and L-PBF, you see a huge difference in pressure drop. I was wondering if, okay, I would say that if it was a real physical phenomenon, the cavitation in the liquid should be almost instantaneous, and it should not depend so much on time, if I may right. But however, the surrounding solid, if you leave a lot of time, it might relax some stresses. And so do you think there is a big difference in strain relaxation in traditional solidification and in fast solidification conditions? And could this explain some of the difference you see in the pressure drop?
Yeah, clearly, I think previously it was way before the RDG model came into existence, people thought that, okay, it's this strain which is affecting the cracks to initiate. But then there were other models which clearly stated that, okay, it's not the strain, it's the strain rate, the rate at which strain is occurring, which is playing a key role into the cracking initiation. So, so if I understood well your question, your comment is that if we change the process, will the effect of strain rate affect to a much extent the cracking tendency?
I have no idea, but I was thinking that if you have a slow solidification condition, then you have you may have some strain relaxation in the solid that will put less strain rate on the liquid films.
True. Yeah, compared to welding, what we have observed that welding has very less strain rate as reported in the literatures, and compared to that in L-PBF, we have based on our small empirical calculation, we found that it is quite high. And to my feeling, I feel that this can play a role, and this is also needed to be studied in detail, I think.
And my last point is about your prediction of solid fraction versus temperature.
Yes.
It's based on Shell-Gulliver.
True.
Do you think Shell-Gulliver is applicable to such conditions? And what is the role of what happens in the liquid, all the Marangoni flow and back diffusion in the liquid and so on, etc. And if you are remelting, what happens in the solid during the cooling down and reheating and so on?
True,
all these parameters, do you think they may play a role?
Yeah, it is a good question. In fact, we had this in mind that, okay, compared to equilibrium conditions at very high solidification velocities, it's better to use the Shell-Gulliver since it can be a better representative of L-PBF for a condition that Shell-Gulliver always predicts the infinite diffusion into the liquid, and you have all the time prediction of microsegregation with Shell-Gulliver. But true that based on high cooling rates, you can have your partition coefficient might be dependent on the solidification velocity. And based on that, we might need to recalculate the Shell-Gulliver considering the partition coefficient is dependent on solidification velocity. And since our dendrites are moving at very high solidification velocity, at the tip of dendrite, you might not have the real exchanges of solute elements. We might not be in the equilibrium state. We might end up having solute trapping at such a high solidification conditions. So we might need to also take that into account while really establishing the solid fraction as a function of temperature curve for our L-PBF conditions.
And is there a way to identify this by making some solid profiles close to grain boundaries? And
yeah, like we can imagine doing simple experiments, doing close to the grain boundaries, simple solid profiles, that which elements are moving into the solid and which elements are particularly localized along the grain boundaries. And based on that, probably we can have an understanding about which elements tend to back diffuse, which element tends to stay in the liquid, etc.
Okay, I step on just the last question, much more general. If I understand well, you with respect to traditional aluminum silicon eutectic or hypoeutectic alloys, 6061 is attractive because it's a structural alloy with mechanical properties. Of course, if it has tracks, it's less attractive. But from what you've seen in the literature, what would be other solutions for this kind of applications where you're looking at, I don't know, maybe conductivity also, I don't know, but also strengths for different aluminum alloys? What have you seen? I guess it should be relatively cheap. I mean, if you start to put scandium and so on, it becomes, and so what from an engineering point of view, if you had to build tomorrow a part in aluminum for structural applications, what would you choose for solution on the bench?
Okay, directly on the bench, what we have.
Well, there has been several proposed solutions to mitigate hot cracking in structural alloys. So from what you've seen, from what you know, from recent works and so on, what do you think is the most promising? I think the most promising way is to achieve for our particular alloy is by using zirconium, for example. I'm not sure about how expensive is zirconium and all, but combining it with different, like for example, we have a PhD student, Matthew, is clearly working on this aspect of this work, addition of zirconium and how much quantity we need to add. So he has shown that just by addition of 2-8% of zirconium, we can have an effect, we can get crack resistant microstructures. So I think economically speaking, this might be not just stupidity, for example, that it's too expensive. Probably we can have this as a particular solution and construct a part using this addition, I think. And then in 5 years, with all your perspectives, we have a new solution which is much better, I'm sure. True. But right at the moment, this is the solution which we have identified in literature, yeah. Okay, thank you very much. I will hand over the mic to my neighbor.
Thank you, Akash. So I'm the first supervisor speaking about, saying a few words about you. So I don't know if I should switch to English or to French or stay in English. I don't know if you, what would you prefer? I can do both anyway.
No problem.
Okay, so let's keep in English then. So the first thing I would like to say is that you had to address a particularly difficult topic, because I have to be honest, from the beginning, I knew that it would be almost impossible to mitigate cracking by playing with the processing parameter. So it was difficult first because we need to find a way and a path to make room and to manage to make room for a real PhD work. So that was the first difficulty we were facing. Mm-hmm. And the second one is that we've decided to include Jean-Marie, that I gratefully acknowledge for coming in this PhD committee, because he is one of the pioneers of this famous hot cracking model. The second thing I would like to tell you, Akash, is that contrary to a lot of PhD students that were working during the current pandemic, I think that for you, this period was extremely beneficial.
True.
Because we had the opportunity to really exchange in a daily basis. And I think that you made huge progress, because you had a lot of results, but you were not taking time, at least not enough at this stage of your PhD, to really go through them and try to draw some conclusion and to get takeaway message. Mm-hmm. So I think that for that, I really want to address you my congratulations, because you made a lot of progress. Regarding the writing of your PhD thesis, it was also quite complicated, because when your contract ends, you were facing new difficulties. So in addition to the pandemic, you were back at home without seeing people every day, without your laptop, with all the software you needed to run the few last calculation you needed. But you managed to finalize your work. And once again, congratulations for that. So to conclude, I just would like to say that I'm very proud of having supervised you partly, because when I see the path followed from the first day of your PhD to today, I'm very proud by all the progresses that were made during these 3.5 years. So really, Akash, congratulations. I wish you the best. And hopefully you will stay in this exciting but highly concurrential world of additive manufacturing.
True.
Thank you.
Thank you for your kind words, Guilhem. In fact,
thank you. So I share what the other Guilhem said previously. Thanks today also for that kind of presentation. I know it was not easy to make that kind of presentation with video conference. I think it's a little stress for you. So thank you, because it was really very nice. And you well prepared this presentation, also technical aspect and also scientific aspects of this presentation. So, like Guilhem said, last 1.5 years was a little bit tricky due to the COVID. So I think we didn't exchange physically like we should have done with a PhD. So we are very sorry. It was not, I think, the best condition. But at the end, I always say to you, it's the end we are seeing, not the previous path. So again, congratulations. Just perhaps some word also, we have talked a lot about science, but you have worked in my lab these 3 years, and I need also to speak about human aspect of a PhD. PhD is not just a purely scientific work. We are prepare you to be efficient in the R&D world. And also human skills are very important. And I think when you arrived in our lab, it was a little bit difficult for you due to the language, the difference of culture. And I think you made a very strong work
to adapt you to French research world, and in particular, CEA world. So I stop with that. And also to be able to motivate people around you to accept your work and to work with you. And it's very nice because it's not the case to all PhD students. So congratulations and thank you very much. And also you, with the other PhD of the lab, which arrived 2 or 3 years ago, you really create with them a very nice dynamic of the lab. It was a very nice period for me to work with you. And thank you again. Just a little bit word also on the beginning of the PhD. So, you know, like Guilhem and Jean-Jacques, it was not easy, the starting of this PhD, due to many aspects which was not your problem, it was our problem. In particular, the aspect of to find a way to conduce like we wanted to characterize sample, because in fact the earth of the PhD finally was almost a fine characterization. And I think me in particular, I have the responsibility to not have been very good in this 4 year of your PhD, because we had a lot of problems. And but despite that, you stay in tune with your PhD. You work very hard. You try to find other solutions. You went to CIMAP also to see if it was better, etc. So in your PhD, you always have problems. It's the earth of a PhD, but I think you manage very well, because for me, honestly, it was not simple the first year also. So, and I think when I see what you presented today, really congratulations, and thank you to have worked with all of three during these 3 years, because at the end, it's a very nice PhD, honestly. And also, it was a pleasure to work with the other Guilhem and Jean-Jacques, because in fact, it was our first PhD in common. So it was very nice to discuss all three about this scientific aspect of this PhD, and the long debates we had all around this 3 years on semantic aspect and scientific aspect. It's also this PhD relation between people. So again, thank you. And I hope we'll find very quickly a good job for you in the R&D sector of activity, Akash. Thanks.
Thank you, Guilhem.
Okay. It's okay?
Sure. If you want, I give you the mic. And
so maybe first of all, I would like to thank the member of the jury, even if one of them is no longer here. First, I would like to thank Aude for participating to this jury, because I know she has a very busy schedule, and this participation is a part of the important relationship that we have between our two institutes. So thank you for this participation, Aude. And as it has been said, it was not easy for Akash to consider that one of the experts on this model will be in the jury, because it's not so easy. So I think your reaction was very nice, because you were not afraid. Maybe you were afraid, but you said, okay, it's a challenge, and it's for me, it will be positive to have this challenge. So I think we must underline that. And of course, I have also to thank you to accepted that. Also underlining the way you manage us, because you had performed kind report, you performed some very constructive suggestions. I think it's very important for Akash. Thank you a lot for that. And of course, also thank you for having made the journey to Grenoble. I don't forget the other member of the jury. I would want to thank Mark, and in particular to thank its flexibility for the choice of the date, because it was a quite hard job. And I know it's not so easy for Mark, because he has another PhD jury this afternoon. So thanks again, Mark, for accepting that. And of course, Alexis also, I thank you to accept the presidency of the jury after the quickest campaign that we can imagine. So thanks a lot. Maybe 2 words about the context of the study. So we have to thank the Institut Carnot for the financial support of that, and the CER, of course. And it is clear that despite our proximity, geographical proximity, thematical proximity, there are not so many common works between our lab and the LITEM. So I think it was a good opportunity also to reinforce the links, and particularly on 3D printing. As that has been said, a large part of the experimental work was carried out here in the CER under the supervision of Guilhem, that I want to thank also, and who has initiated this work. And I think we have quite well worked together during the three years. Of course, I have also, before I would speak about you, but I have also to say some words about the other Guilhem. One difficulty of the study was to manage 2 Guilhems, because Guilhem is not so well, it's quite rare. And here there are 2 Guilhems in the supervision. And it was very difficult for me to say that Guilhem 1 and Guilhem 2, because it's quite a tricky problem. So for Guilhem Martin, my colleague, of course I have to repeat that I repeat systematically in co-supervision with him. It's a particularly great chance to have the opportunity to co-supervise with Guilhem. In fact, when we say co-supervise, it means that he made 99% of the work and me the rest. So it is particularly true, I think, for your thesis, Akash, because I think that Guilhem made more than a decisive contribution in the orientation of the work. So
I completely agree with this.
With that, but for me, it's clear. So thanks again, of course, Guilhem. So Akash, maybe some words about your trajectory. So you arrived after you've been in Bangalore, you arrived in Grenoble, maybe 5 or 6 years ago, yeah. In Felma.
2015.
Yeah, I remember that I was a student, I remember, yeah, okay. After that, you go to in Germany, and you have some experience in Constellium, in Airbus, and then you started your thesis. And as that has been already said, I would like to underline your human qualities. Your capacity also to, I don't know how to say that, but to maintain, I mentioned an equal temperament, whatever the situation. And the situation sometimes was not so easy, because there were some practical difficulties to access to some equipment, something like that. Not so easy to manage also 3 supervisors, which can have contradictory advices and something like that. And all the time, you were able to manage that very nicely. And it was not so easy. Not so easy also to interact with different structures, which have different ways of working. And again, you manage that very well. And I would like also to underline something. You made the effort to learn French. And I think it reveals something from you. It reveals that you have an open mind, that you have a constant desire to improve yourself. And I think it's very, very important to know that. And concerning the subject, I think also I want to say something, because of course there is a lot of work today about additive manufacturing of aluminum alloys. There are obviously a widely shared strategy about the modification of composition. There's a lot of work here, in our lab, in anywhere. But I think it's very interesting to have the tools that you develop in order to see if, maybe in the future, maybe not today, but with new machines, or if it could be possible to reduce the crack sensitivity on well-known and widely used alloys. Mm-hmm. Because it's a very tricky topic to modify composition and to propose new alloys. But considering that with the old alloys, I would say the old world, maybe today with machine which cannot satisfy the conditions, but maybe tomorrow we don't know. So I think these tools will be very important for the future, and it is your tool. So finally, I would like to say that it was very nice to work with you. I know that your professional future looks quite very well. So yeah, I'm very happy. I wish you the best for you. I hope we will keep in touch. And so I just say thank you for the 3 years, Akash.
Thank you very much, everyone, for these kind words. In fact, if it's okay, I can also share some of my views quickly, or...
I would prefer that you do that after the deliberation. We still have to deliberate. Okay, so we have to... Okay, so now it's done. Okay. So, Akash, we'd first like to congratulate you for a very, very nice presentation. And you've demonstrated today that you are not only a good researcher, but you're also a good teacher. You did a fantastic presentation, very clear, that made people understand your work. And we can see that you enjoy that people understand your work and enjoy this communication. So that's very, very good. On your research work, all the comments have been that you've done a huge amount of work that was really good on a long-term perspective of understanding how to deal with defects in L-PBF. So this is not the easiest work to do. It's not only trying to what works, what doesn't work, but it's also really going into the physics to understand how to control the different phenomena that lead to defects, to cracks. And on the long term, it's important to do this work, and you put some foundations of future work that are really important. So you did that with a lot of good character. Everyone was really happy in the way you've integrated into teams and worked with the different people. So for all this, we congratulate you. And the way you've responded to the questions you showed that you master your subject. There are lots of questions in different areas, and it was quite easy to have a scientific discussion showing that you are really a mature researcher now. So for all these reasons, we congratulate you, and we attribute you the grade of Doctor of University Grenoble Alps. I never remember the specialty, but in materials mechanics, civil engineering, and electrochemistry. Thank you.
Everyone for being physically present. So we know that it's quite difficult times we are going through, and finally making it. It was a big pleasure for me to present in front of everyone the masters of field, the creator of the model, Professor DREZET, the experts, Dr. Guilhem MARTIN, Professor Jean-Jacques BLANDIN, Professor Alexis and Dr. Guilhem ROUX, experts in different fields, and presenting in front of them, for me it was a real honor, and I really enjoyed the process of this preparation, going into, like, if I remember well, when I came in 2015, quand j'ai arrivé première fois en France, j'ai jamais parlé français, et it's because of the team, and it's because everyone was so collaborative and helping in nature that I enjoyed my work, and I enjoyed the presence of people around me, and this really helped me to grow in not only professional but in my personal life as well. Like the first year of PhD, if I remember well, that we were having quite difficult times. We went through different aspects in which we couldn't really understand what is happening into our material. I was a bit lost for the first year of the PhD, but when I came to know from Guilhem MARTIN that okay, we can look into this model, there is this particular type of model called Rapaz-Rosé-Grumet model, and which we can start to think about it. He was the first time who he introduced me to the model, and I said, okay, let's give it a start, a new start to my PhD in that aspect. This really, I think, was the turning point of my PhD, that we looked into the modeling aspect of the work and we start to make progress into it. And I really thank Guilhem for introducing me to this this aspect of the work, which is also very important, that he made me really understand what are the key points to be chosen, what is the observations to be made, how to be done as a researcher. There was huge work of Guilhem as well in my PhD to have day-to-day contacts with each other, to managing me with doing experiments in CMTC, doing experiments in CA here. It was a bit challenging administratively initially, but Guilhem, he took the responsibility of everything to take care of that, and having time-to-time discussion with Guilhem was very fruitful. And thank you for Guilhem for being there as a sole mentor in CA, which I really appreciate. There was a role of Professor Blondeau. He was like every meeting, when we used to visit CMAP, sometimes he used to be a bit lost. Akash, c'est quoi exactement, tu dois parler exactement. So he wanted to have an understanding of what is going on. So initially, I think I had a bit of troubles to do that, explaining things in a scientific way. But as time progressed, I found that his suggestions, his way of seeing things, it really helped me to consolidate my work as well. So I really would like to thank Professor Jean-Jacques BLANDIN that you gave me that direction to work on, and under your direction I was able to perform this thesis. So really thank you for you and for your time which you have given me, time to time. Thank you very much. And I would like to thank Professor DREZET for being physically present here and having a fruitful discussion with me on the topic. In fact, since I was a bit initially stressed, since you are the creator of model and I will be defending in front of you, so I had to be well prepared, otherwise I might be into the wrong foot. So, yeah, so the model was made 21 years back, and the way we used it, I think it was the key point as well of the thesis, that extracting the most from the model and putting it into the difficult conditions in 3D printing, in the most difficult conditions which the model has not been explored yet. So I think the journey of using RDG model for me was the heart of the thesis, and it made really me understand the cracking aspect into the details. And really would like to thank you for generating this model so that I could use it and have my PhD. So thank you for that. Thank you, Professor Alexis, for being here, and we know that you are an expert in aluminium, and fortunately I didn't have a lot of tough questions from you, but probably you might have it to ask. So I would like to have future discussions in case. Thank you, everyone. And last but not the least, my parents. I would like to thank my mom. In fact, just to give a few words about my mother, she was a mathematician, and she trained me from childhood to be to study a bit of mathematics. And from my childhood, I was a bit capable enough to understand mathematical problems. And because of her, I was motivated to pursue a bit of science as well. And speaking about my dad, he comes from a not that stable family, and because of him, in India, he could make me and my sister raise up in India in good conditions, good education facilities. So I would like to thank my dad for giving me all the conditions to raise me, and my parents, they have sacrificed a lot. And my sister as well, she used to be motivating all the time to me. And the presence of all the friends here, right from Charlotte, Claudia, having time to time discussions in the meeting room in our labo. Thibaut, my colloque, the best colloque, right now, Manu, everyone, Elisa, everyone, Matthew and Florian, the next future PhDs. I hope they got motivated because of working with me. So I wish you best of luck, everyone, and yeah, that's up. And thank you, everyone, for being there with me in this wonderful occasion. And really, thank you, everyone. Yeah.
Du coup, nous aussi, on a un petit truc pour toi. Maintenant que tu es docteur, là, on va pouvoir. Tu as le chapeau qui va avec.
Oh.
Merci beaucoup.
Merci beaucoup. C'est très gentil.
Et donc, un petit présent avec tout le monde chacun pour toi et félicitations à tous les Tu ouvres tes cadeaux à table ou pas?
In fact, maybe we can go outside and check. Thanks everyone for being present on the Zoom call. Thanks for accompanying this session. Thank you. I'm quitting the. Thank you, Professor Aude and Dr. Mark Thomas for being present in the jury and giving significant insights into the questioning of the discussion. Yeah, it helped me to understand everything. Thank you very much. Yeah.
Je dois partir dans un quart d'heure.
Oui, j'ai prévu. Maybe we can go outside a bit because having a small pot in the Bathimos is the answer. Du coup, on peut aller extérieurement. Et